Hello and welcome. In this video, we want to take a look at a notion that expands our idea of an integral to being an integral over sort of arbitrary curves in the plane or even arbitrary curves in space eventually. We call these line integrals. Now let's take a closer look at this picture to get the basic idea. So here's the basic setup. We have a curve that's going to start at, it doesn't actually matter, but let's just for the sake of being, say we have this parameterized so that it starts here and it ends over there. It could go the other way, but just the point I want to make here is that this is not just a curve where y is a function of x, that there's places, some values of x here where there's multiple values of y on this curve. So this is a parametric curve. But I've got some function of two variables, and what I want to do is I want to take this curve that's in the xy plane and I want to cut it up into a bunch of little pieces. Okay. This is not uncommon when we're doing the notion of an integral, right? You cut it up into a bunch of little pieces. Now, on each one of those pieces, I want to select a point. It could be any point along that little interval. So this would be the point x1, y1 star, right? This is the special point on that first interval. And then you pick a point down here on the next interval, which would be x2, y2 star, right? Or x2 star, y2 star. Anyway, you're picking these points on each one of those intervals. So then what I want to do, just like we did with integrals before, is I want to take each one of those points and evaluate the function. So I'm going to have f of x1 star, y1 star, and I want to multiply that by the length of that first little interval. Well, the length of that first little interval I'm going to call, let's say, delta S1. Right. And then I'm going to do the same thing with the next interval. I'm going to do the function value of x2 star, y2 star, times delta S2, and keep doing that for each little interval until I get to the last one, which would be x, let's say n star, y n star, times delta Sn. Right? And what I should get there is very similar to what I got when I was doing, the integrals back in Calc 2. Each little length is being multiplied by a height, and the height is calculated by plugging one point into the function, and then that height times the length is a little bit of area, and you're adding up a whole bunch of little bits of area. And then, of course, we're going to take the limit as n goes to infinity. Now, before I go on, I want to emphasize the fact that I was using here these little delta s's, delta s1. I didn't say delta x or delta y or even delta t if I'm thinking of this as a parametrized curve, which of course I am. These delta s's are little bits of arc length that actually measure how long is that curve. And you may recall back in Calc 3 we did have a notion of how to calculate arc length of a parametrized curve. Right? So these little bits of arc length are being multiplied by these heights. Okay, so it's not delta x, it's not delta y, it's not delta t, it's delta s. It's little bits of arc length. Okay, so here's the definition for a line integral. Right, given a function f of xy and a parametrized curve, which we have a parameterization here of it, r of t is x of t comma y of t for t on some interval from a to b, then we define the line integral to be the limit as n goes to infinity, the sum I equals 1 to n of this f of xi star comma yi star times delta si. Okay. Now there's, there would be some work to be done showing that this is well defined, that as long as the delta si's are all going to 0, then this limit does exist, and the various conditions, right? The function would have to be continuous, the delta xi's would all have to be going to 0, and then you get a limit, and it would be what we would consider the line integral along that curve of that function. Okay, but we don't want to have to do this limit every time, so we're going to have, of course, a simpler way to do it, just as we had in Calc 2. And what we do is the following. So you're given a function f of xy, and you got this parameterized curve for t on the interval from a to b. Then the line integral will be equal to this. So you're going to take the x and y of the function, plug it into f, x and y of the parameterization, plug it into x, and then the ds is going to turn into the length of r prime of t times dt, right? Remember back in Calc 3, when we figured out what arc length was, it was the integral of, essentially the integral of the speed, right? If you think of r of t as a position function, then r prime is the velocity function, and the length of r prime is the speed. So speed times a little bit of time is a little bit of distance. That's the arc length. So the ds is the length of r prime of t dt. Okay. Now, another way to write it here is like this, and I'm falling off the page just a little bit here. Can I view that? There we go. The integral from a to b of f of x of t, y of t, times, that's not a dot product, that's a times, the square root of x prime squared plus y prime squared dt. Okay. Now, I'm going to point out right now that generally this is not an easy integral to solve by hand. However, it is a single definite integral. And your calculators can do that. And I am encouraging you to use your calculator to do this. Once in a while, you get a simple enough one to do it by hand. The textbooks generally are reasonably good about giving homework problems where you can do them by hand if you want to. But I'm not so careful on quizzes and test questions. I want to see that you set them up properly. And then, of course, I want to see that you can plug them into your calculator as well properly, but I don't necessarily need to see every step of how you are doing the integrals, techniques or whatnot. Okay, so here's an example. I've got r of t is 4 cos t, comma 3 sine t. So this is, it would be an ellipse, going back and forth, centered at the origin, back and forth 4 in the x direction and 3 in the y direction. But I'm only going to use the interval from 0 to pi, which is going to be the top half of the ellipse. Okay. I'm calculating r prime of t just because I know I'm going to need it here. So the derivative here would be minus 4 sine t and 3 cos t. And the integral that I want to integrate is 25 minus x squared minus y squared ds. Okay. So plugging stuff in here, the 25's there. The x squared is going to be 4 cos t all squared, so 16 cos squared t. And then minus y, so that's just minus 3 sine t. Be careful here, and that should all be in parentheses, because that whole thing has to be multiplied by this little bit of speed here, right? So the square root of 16. So this is, when I'm setting these up, I make this mistake so often that I forget to take the derivative, and I just use those things, square them and add them up, and so I'm not doing the length of r prime, I'm doing the length of r, which of course is wrong. So take the derivative, and then, so square this, 16 sine squared t, square that, 9 cos squared t, add them up, take the square root, times dt. And I'm integrating from 0 to pi, which turns out to be 172 and some change. Right? So this would be essentially the area over this curve underneath this function. I'll draw a picture of it here in a minute. I want to take a look at another example, which is actually very much the same example. In fact, I'm going to leave that one on so you can see. I'm taking now the curve being 4 cos 2t, 3 sine 2t, which is actually the same ellipse. And I'm going to take it, sorry, it's the same ellipse, but it's going around twice as fast, right? Because of the 2t's in there. But I'm only going to take it from 0 to pi over 2 instead of where I had 0 to pi before. So I'm still looking at the top part of the curve, the top part of that ellipse. And I want to see if there's any difference in integrating over it I'm integrating over exactly the same curve, but with a different parameterization. Okay. Now, again, I'm going to need r prime, so I'll take the derivative. Remember, there's a chain rule now. These 2's pop out to get the derivative there. I'm going to integrate exactly the same function as before. So plugging in, the x is now 4 cos 2t, so 16 cos squared 2t, and the y is 3 sine 2t. The derivatives, the derivative, the velocity part of this, the speed part of this, is quite a bit different because instead of just a 4, that's now an 8, and instead of a 3, that's a 6. So I got 64 sine squared 2t plus 36 cos squared 2t dt, and I'm only integrating from 0 to pi over 2. It turns out that you get exactly the same answer. Is this a coincidence? Well, as it turns out, no, it's not a coincidence, although there are some conditions we need to talk about. One of the things that's going on here is if you can trace out that curve exactly once, then it doesn't matter what parameterization you use. In fact, you can even go over it backwards if you want. Again, I got to be a little careful. There's 2 ways to go over the curve backwards. Like on this first parameterization, I was going from 0 to pi. T equals 0 to t equals pi. Now I could run that integral pi to 0, which is running the t's backwards. In that case, I would get I'd get a minus sign out in front when I did the integral. I could, however, parameterize it to just go the other way. With t increasing, it would just cross it in the other direction. And in that case, I would still end up with a positive 172 rather than the negative, because when I'm finding this arc length, this square root of x prime squared plus y prime squared is always positive because it's the positive square root. So it's like I'm always thinking about moving forward. And this is where I need to make sure that my parameterization doesn't double back on itself. If I had a parameterization that went sort of up and then back and then forward again, you might have a stretch where you covered it going one way and then back across, going backwards and then going forward again. Now, if the going backwards actually counted as negative, then you'd add it in, you'd subtract it out, you'd add it back in again, and it would be okay. But it's not counted as negative because this square root doesn't become negative just because you're moving backwards, right? So when we parameterize the curves, we got to make sure that we traverse that curve only once, right? And we don't double back on any part of it. Okay. If you do that, then you're going to have the same result no matter how you parameterize that curve. Okay. Here's the picture. Here's the geometry of this problem. There's the static image. Down here in the xy plane is the curve that we start with, and I have little arrows drawn to indicate that it's, that's the direction we're moving in. The sort of upside down parabola surface is the 25 minus x squared minus y, and the purple pinkish region here is a surface that is just straight up, just parallel to the z-axis above that curve, but is bounded on the top by that blue parabola surface. We are calculating with this line integral, we are calculating the area of that, whatever color you want to call it, magenta, let's say, maybe pinkish purple. That thing, you got the length, little bits of arc length times heights, little bit of arc length times height, little bit of arc length times height, and you get the area of that surface. Let me see if I can pull this up. It should load in CalcPlot 3D. Yeah. So in CalcPlot 3D, you can move this around, take a look at it from different angles. You can see the curve in the XY plane. It's upside down right now, so it looks like I'm doing the bottom part, but it's actually the top part. Yeah. And you can see this surface, which is directly above the curve, and we're calculating its area. Now, I want to finish up this video with just mentioning we can do exactly the same thing in R3. So if you happen to have a function of three variables, f of x, y, and z, and you got a parameterized curve in 3 space, so r of t is x of t comma y of t comma z of t for t on the interval from a to b, then we can talk about the line integral of f along that curve. And this part looks exactly the same. It's going to be the function with the points on the curve plugged in times a little bit of arc length. And that little bit of arc length is the length of the velocity vector times dt. Okay, and so here you go. I'm still off the page. I like it sometimes to say that, oh man, this is just so good, it's off the page. So I'm going to move this over a little bit so you can see that. There we go. Yeah. So you got to plug in x of t, y of t, and z of t into the function f. You then have to multiply, sorry, this is not a dot product, and you multiply by the square root of x prime squared plus y prime squared plus c times z prime squared dt. Okay, it's exactly the same thing, just one more coordinate. Geometrically, this looks a little bit different because, you know, when I think about this picture right here, where I have this area above the curve, well, I have a three-dimensional curve, you know, a curve in three-dimensional space, and then the area above it is in the fourth direction, right? So you got to think of w, x, y, and z. And so for each point over the curve defined by this r of t, in the w direction, you move a height that's calculated by that f of t. So it's a little bit harder to visualize, but it is still just a surface. But this surface is now out in 4 space somewhere. It's still just, it's a two-dimensional curved surface, and you're just finding the area of that surface. It's just hard to picture exactly where it is. So anyway, this is the basic notion of a line integral of a scalar function over a curve.